And I'm starting also recording it here. Okay, it should work now. Yeah, all right guys, so this is going to be lecture 9, and first off we're going to talk about stationarity again. If we consider the first order autoregressive process, I'm kind of repeating what we have done last time. It is going to be stationary. This is basically the notation with the Lac polynomials. The Lac polynomial is simply 1 minus AL, and the following statements are equivalent. The process is stationary, and this means if and only if, and that's what you also heard, the absolute value of A is less than 1. This is what we had done last week. So this is the condition that we established last week, and we simply just ignore the structure of time. So I told you before, we're going to look at stationarity from the practical perspective and from the practical perspective only. So that's basically what it's going to be. Okay. Now the second is, and this is what we have established yesterday, that the roots of the Lac polynomial have absolute values which are greater than 1. I mean, if there is just a first order autoregressive process, that means that there is just only one root. Okay, so I said roots because I wanted to generalize that. So, but in case of the first order autoregressive process, there is just one root actually, because it's a linear function. Okay, but it's going to be like this. So if z is a root, that means Nullstelle, right? So that's a German term, then the absolute value of z is going to be greater than 1. This means that the roots are outside of the unit circle. You might remember this. Okay, so you have the complex plane, this is the real part of a number, and this is the imaginary part of a number, and here you have 1. So there is going to be a circle, okay, with the radius 1, and if you're outside of the circle regarding the roots, okay, just like that, then you have stationarity, and with every single root that must be the case. If you have a second order process, there is 2 roots in general. And if they are complex, they are the so-called complex conjugate by each other. So if basically A plus I times B is 1, then the other one is going to be A minus I times B, where I is basically the square root of 1. You heard that, right? So one is the complex conjugate of the another. Anyways, okay, so we're going to see that later on. Okay, and then we have basically the third condition, which means that the Lac polynomial is invertible. Okay, so that must be invertible, and that is going to be the case if the process is stationary, and I'm going to basically show you how to find those coefficients if you want to establish stationarity in terms of a first order autoregressive process. And just remind you, I'm going to give you one assignment where you have to do that for a higher order process as well. Okay, so you would need to establish that stuff for a higher order process already. Okay, that's something that you would have to do. Okay, please let me check the options. I'm kind of freaked out because sometimes the recording does not work, but it seemed to work now. Okay, all right. So we are going to generalize that concept for higher order processes as well. Actually what we did that, and that was stay. Of course, the last condition will drop basically because there is no parameter A, let's say. Okay, you have multiple parameters, and actually the combination of these parameters will decide whether the process is stationary or not regarding the roots of the Lac polynomial. And the second is that the Lac polynomial is invertible. So if the inverse is finite, that means that it's going to be invertible. And I told you before why this is, because then after that it's just simply the process can be written as simply just a linear combination of the noise. So you have basically 1 by the inverse of the Lac polynomial times observations of the noise, and the noise is stationary. So if the inverse exists, which means that it's going to be finite, then the process is going to be stationary. This is what we have established yesterday. I just wanted to kind of repeat that, okay? And I'm going to show you some examples, implications, stuff like that. And based on that, I will give you your next assignment, which is going to be about actually finding out whether the process is stationary or not, okay, from a given processes. Keep in mind that the root can be complex, okay, so you have complex numbers involved, and I'm also going to show you how to calculate the absolute value of a complex number. But if we are in a complex plane, we just simply use the Euclidean norm, okay, so that's what we're going to use. All right, now let me look at that. So see what basically what it would be. The first order autoregressive process is stationary if and only if, so that goes both ways. The absolute value of the parameter a is less than 1. The lag polynomial, as I mentioned before, in the first order autoregressive process is simply just 1 minus al. And then you have the representation for which we use the inverse of the lag polynomial. So we have figured it out that it's going to be 1 by a1. Okay, so you have basically the lag polynomial. In the denominator, you have the lag polynomial at point 1. Why this is? Because it's applied on a constant. All right, so if it's applied on a constant, the lag operator will disappear, which means that it's going to be just equal to 1, of course. So that's what I was saying. Okay, so you have seen this, and actually this is going to be 1 times a constant. So whenever basically the lag operator is considered, even if it's the inverse, then you would need to just know that if it's applied on a constant, which it is, then it's simply just going to disappear. That's it. I mean, if I say disappear, I don't mean 0, it's going to be 1. All right, even if it's going to be inverse. I was showing you that last time. And then, therefore, okay, you have 1 by the inverse of the lag polynomial on the noise. And as you see, the noise becomes kind of a linear transformation of basically the process becomes kind of a linear transformation of these noises because there are multiple ones when it comes to inverse. In case of a first order autoregressive process, you know from geometric series that the limit of a geometric series is going to be 1 by 1 minus q if basically q is the base for these members, if and only if the absolute value of q is less than 1. So that series would exist if and only if the absolute value of a is less than 1. As you see, the inverse exists if and only if the process is stationary, literally speaking. That's it. Okay? And if that is going to be the case, though, then you find the coefficients actually as follows. So you look at this structure, you can simply ignore the lag operator if you like. Okay, so I mean, you can simply just keep that out, okay, because this is going to be applied on the noise. So wherever you have the noise involved, the lag operator, let's say times the noise, although it's just a pseudo multiplication, becomes the noise at time point t minus j if you have basically j as an exponent. Okay, so all you would need to look at are these coefficients. Okay, so a to the power of j, whereas basically alpha j is going to be a to the power of j then. So alpha 0 is going to be a to the power of 0, alpha 1 is going to be a to the power of 1, alpha 2 is going to be a to the power of 2, and so on. This is a way basically to identify these coefficients. You do not need the Taylor series expansion in this case. Okay, so there is no necessity because this is the Taylor series, right? So that is basically a specific case of the Taylor series around the point 0, if you basically consider that. Okay, so that's a simple, actually this is a simple expression because everybody knows that, you know, the limit of the generic series is going to look like this. So you don't need the Taylor expansion here to find those coefficients. One of your assignment is going to be just that. But if you don't know how the limit basically of this series would work, you would need to find the inverse of the lag polynomial by differentiation. Okay, so I'm going to show you how to put that together when it comes to the Taylor series. Okay, now we just assume that we wish to find the inverse of the lag polynomial. We're going to see that basically the lag polynomial is, I mean, this is the inverse of the lag polynomial 1 by 1 minus ax, okay, if it's basically a function of x. So keep in mind that a of x is 1 minus ax, okay, this is what it would be. And we would do, but that's not the inverse already because this is equal to this sum of these coefficients, right? So alpha j times the noises at time point t minus j, where j starts at point 0 and plus infinity. So basically the goal would be finding those alphas because these are going to be the coefficients that are attached to these noises. And based on that, you would need to address basically what the variance of the process would be. Okay, so you could do that one. Anyways, okay, so I'm going to show you how to in a general case, but let's pretend basically, I mean, we don't know. Okay, so in general, we don't know what it would be. This is going to be 1 minus 1 times, 8 times x to the power of minus 1, as you see. And the reason why I basically are using this structure is because you need the derivatives for the Taylor series expansion, and it's much more easier to differentiate with this structure than using that one. Okay, so here In the former, you would need the quotient rule. Here, I just need the chain rule, but it's going to be easy because this is a power function. Okay, so differentiating a power function is easier than differentiating a quotient, okay, in general terms. I'm going to show you how this works. So let's find the derivatives. That's what you would need to do. Okay, so you simply take the inverse, find the derivatives, and then you put them together with the Taylor series. I'm going to show you how to. So the first, you know what differentiation is, guys, right? So you need to find the derivatives of the function. Okay, so that's going to be the first derivative. Now, if you apply the chain rule, you take first the other derivative of basically, let's say, I call it other derivative of the other function. That's step number one. According to the chain rule, this is it. So basically, if you differentiate x to the power of -1 with respect to x, this becomes actually -1 times x to the power of -2. I think everybody knows this. Okay, so that's what I was using. Second step, according to the chain rule, you put in the inner function into that derivative, and the third step is you multiply that by the inner derivative. So what's going to be the inner derivative of 1 minus a times x with respect to x? This is going to be negative a, of course. So this is something that you would need to multiply that with. Okay, and then you kind of basically rearrange that stuff. I'm going to collect those and using induction to find a general basically formula for, let's say, the nth derivative, but I'm going to use the second derivative here. So take that and differentiate that with respect to x again. You need to find the chain, basically by the chain rule, there is a constant, so it literally says constant times a function. If you differentiate that, this becomes constant times the derivative of a function. So you simply take a and differentiate 1 minus 8ax to the power of -2. This is what you would do, okay? And this is going to be -2 times a times 1 minus a to the power of a times x to the power of -3. So keep in mind, guys, this is the other derivative of the other function, okay? That's going to be step number one. Step number two, you put in the inner function into that other derivative. This is going to be basically -2 times a times, in parentheses, 1 minus ax to the power of -3. And then you multiply, this is going to be the third step, you multiply that by the inner derivative. So you take that function and then you multiply that, basically the whole thing, by the inner derivative. This is going to be -a again. All right, so because the inner derivative of the inner function is going to be always the same. So, and then you kind of rearrange that stuff. So you see, you have a times a, because that's becoming a squared, and then you have -2 times -1 is going to be 2. So this is going to be 2 times a squared times, and then the brackets to the power of -3. So now from this structure, you kind of basically know how this is going to evolve. Okay, so if you take the third derivative, this is going to be 3 times 2 times 1, basically, times a to the power of 3 times 1 minus ax to the power of -4. Okay, so this is going to be basically the further structure when it comes to the third derivative, and that's what you see here. This is goes basically the factorial of 3. You know the term factorial, right? So factorial of 3 is 3 times 2 times 1. Factorial of 4 is going to be 4 times 3 times 2, and so on. The fourth derivative, which I'm basically expressing like this, accordingly is going to be the factorial of 4 times a to the power of 4, I think, right? So that's going to be times 1 minus ax to the power of -5. Okay, so this is basically, you know, how using induction you can find basically the derivatives. I'm just going to give you another one. Okay, so as I mentioned before, the third derivative, just take that. The other derivative is going to be -3 times 2 times a squared times 1 minus, I mean, you need the brackets to the power of -4 because, you know, you need to subtract 1 from the exponent. This is going to be step number 1. Step number 2, you put in the inner function into that derivative, which is going to be, I mean, you use the brackets, so inside the brackets you got 1 minus ax. And then you multiply that by the inner derivative, which is -a again. And that's going to be equal to, and just as I said before, 3 times 2 times a to the power of 3 times 1 minus ax to the power of negative 4. The reason why I don't multiply that or don't calculate this result, because I recognize that this is going to be equal to the factorial of 3, okay, as a factor. So this helps you to generalize that derivative. Therefore, the nth derivative, as you see, the n derivative is going to be, as you see, the factorial of n times a to the power of n times, and then you have 1 minus ax to the power of minus, and then you have n minus 1, which is basically, you know, you can put it like this, but I would simply use minus n minus 1, and that's it. You need to subtract basically 1 from the exponent, and this is what it's going to be like, okay? It's not a big deal, guys. It's not rocket science, you know, so this is how you would generalize it. Try to do that. Actually, when I give you a process, then you would need to find basically the inverse of the Lac polynomial, then you would need to try to put that together. So this is basically what the structure of that is going to be. Now this helps me, okay, so everybody understands how I come up with the nth derivative. Okay, so these are going to be the derivatives, so n can be anything actually from the set of natural numbers, although it's going to be finite, right? But in this case, you can also have infinitely many times. So you need to assume that the function is going to be differentiable infinitely many times, but that's always going to be the case. Okay, so because any Lac polynomial of AR processes, so whatever the process is, even if it's basically ARP, the inverse of a Lac polynomial of an ARP process is going to be also infinitely many times. It's going to be differentiable infinitely many times, and this is basically required to apply the Taylor series. Okay, so let's say the regular type of functions, or the elementary functions, which are always going to be like this. The hyperbola is also an elementary function, believe it or not. Is always going to be differentiable infinitely many times. You take basically the Taylor series around the point 0, which basically equals that expression. Okay, so you simply just basically take the nth derivative of the function, plug in 0. You need to understand, you plug in 0, divided by the factorial of n. So that means that, you know, the factorial of n is going to be canceled out from this expression, as you will see. Okay, that's going to happen actually basically for every single expression there is, but doesn't matter. And then you'd have basically times x to the power of n, and that's it. Okay, so this is basically how it will look like. And then I was basically just, you know, putting everything together. First, you put in the derivative, which is the nth derivative at point 0. Now, if you basically calculate the nth derivative at point 0, then this is very easy, because this expression here, x, is going to become 0. Okay, so that's actually not that bad. And that will yield basically the factorial of n times a to the power of n times 1 minus 0 to the power of n minus 1, which is going to be just that. Okay, so this is what you're left with. And yeah, that's kind of cool, right? So this is basically what it is. Okay, I mean, but I was using that in detail. Okay, keep in mind that the base of this power is going to be equal to 1. So whatever basically n is, it doesn't really matter, because it will just simply cancel out, and that's going to be the final expression. And here you are. Okay, so even if you put that together, you see what these coefficients are. Okay, so here you need to set this equal to these alphas. Okay, so that's basically, we know what these alphas are. So alpha j times, let's say, x to the power of j, where j, or n actually, but that's the same. Or you can write it like this. Maybe it's more consistent if I use n as the summation index, just as I did it before. Okay, so this is what it's going to be. And then n starts at point 0, and then it will just, you know, you would need to take the convergence. So this identifies these coefficients immediately. And these alphas are actually unique for every AR process. Okay, so these are the alphas that you would need to find. And I'm going to give you, let's say, a process which is a little bit more complicated than that. And I would like you to ask you to find those coefficients. And based on that, you would need to look at what the expectation, what the variance, and maybe what the autocovariance of the process would be. This is the way to do it. Again, but in this case, for the first order process, you don't need to, because everybody knows what the limit of the geometric series would be. Okay, so this limit basically exists, okay, if and only if actually the absolute value of q, which is the base of this of the corresponding member from the geometric series is less than 1. All right, so in this case, for the first order autoregressive model, you don't need the Taylor series expansion, but I was showing you that anyway, so when it comes to a more complicated process, let's say, you would be able to set this together on your own, which you would need to. Okay, so I'm going to ask you to do this, and that's going to be one of your next assignments. Okay, not this one, but the following one, the one after that. Okay, and yeah, maybe maybe you get away with it. So if you're kind of smart, you can basically get away with that. Okay, so you would need to basically just consider, but again, it doesn't matter. So as long as you identify the coefficients, I'm cool, okay, which they are here. These are these alphas, okay, so this is alpha, and alpha 0 is 1, all right, because a to the power of 1 is going to be 1, as you see. Okay, what is a? Again, a is the parameter for the autoregressive model. So this is basically the slope coefficient. That's what I'm talking about. So here is a. That's the one. All right, so here it is. A to the power of 0 is the first. A to the power of 1 is the second. A to the power of the 3 is the third. And so on and so on. All right, guys, is it clear? So that's the mechanism that is applied. Now, I'm going to look at stationarity of second-order processes. Okay, how would you identify whether a second-order autoregressive process is stationary or not? This is not difficult, guys. You would need just to solve a quadratic equation, but keep in mind there is 2 solutions in general if you look at the complex plane. Now, the example that I brought with me is going to yield real roots. Okay, so there's no example involved which has complex roots, but when it comes to complex roots, I'm going to show you what to do. So basically, you need to set up the Lag polynomial first. Keep in mind, guys, that the Lag polynomial is always attached to the process, which yields basically the constant plus the noise. That's always the structure. So in this case, the Lag polynomial is always going to be 1 minus a1l minus a2l squared. Now, what is a1 and a2? Okay, so here you see what a1 and a2 is. If basically the structure of the process is that you have v plus a1 yt minus 1 plus a2 yt minus 2 plus the noise. Okay, so this is basically, consistent with that. So in this case, a1 is equal to 0.3 and a2 is going to be equal to 0.1. But you could start basically, you don't need to put that in general terms. This is what it's going to be. So a1 minus a1l, which is 0.3l, and then minus a2l, which is 0.1l squared. Sorry, minus a2l squared. Sorry, guys. And this is what you would have. All right? So keep in mind, guys, a1 is 0.3 and a2 is 0.1. Okay? This is the Lag polynomial, and then you would need to find the roots of the Lag polynomial, which I'm going to basically show you how to. Okay, so if let's say z is a root, which means Nullstelle in German. So that means if you put that into the function, you get 0 all the time. So let's say z, we call it z. It's not the Lag operator. The Lag operator is not 0, okay, because it doesn't exist, by the way. But let's say the polynomial does. So if you basically put the z, which is the root, inside, you get 0. So that means that 1 minus 0.3 times z minus 0.1 times z squared is going to be 0. I was just rearranging that term because that expression because you need to show or need to see that this is a quadratic equation that you would need to solve. Now, for aesthetic reasons, this is something that you don't have to do, but for aesthetic reasons, since I want to get rid of that, I was multiplying everything by negative 10. You don't need to do this, okay, when it's solving the quadratic equations. German people do it because there is a so-called PQ formula that requires just only 2 parameters, but in general terms there is 3. So everybody knows the formula, right? ax squared plus bx plus c equals 0. Then you have basically for the roots minus b plus minus the square root of b squared minus 4 times a times c divided by 2a. All right, so that's the quadratic equation in the international version, but there is also a German version. Let me give you that one because this requires the normalization of the first coefficient. Okay, so you have x squared plus p times x plus q being equal to 0. This is going to be where you have negative p by 2 plus minus p by 2 squared minus q. So that's basically the normalized version that only requires 2 parameters. Choose either of the two. Okay, so show hands who has seen this formula at school. Okay, so you probably studied in Germany, right? And in Poland, which one is applied? The other one? The first one. All right, so okay, you can use that. You can use either of the two. The reason why I wanted to basically have included both more or less is actually because, you know, in Germany you would need to normalize the first coefficient, which means that it's supposed to be equal to 1, so that you can get rid of that by simply just multiplying it by negative 10, but you don't need to. Okay, so for aesthetic reasons I do. Okay, so then of course you have basically A is going to be equal to 1, B is going to be 3, and C is going to be minus 10. All right, so according to that, and therefore just simply you plug it in, okay, which I do. So you have, I mean, you need those roots. There is 2 in general, so 1 and 2, okay, the first one and the second one. For the first one you use plus, and for the second one you use minus. So you have minus b, which is minus 3, plus minus the square root of b squared, which is 9, minus 4 times a, which is 1, times c, which is negative 10. So you got 49 under the square root, which is going to be 7 then. So, and this is divided by 2 times 1, which is 2. So you have negative 3 plus minus 7 divided by 2. So that generates basically 2 roots. The first one is going to be negative 3 plus 7, which is 4 divided by 2 is going to be 2. And the second one is going to yield negative 3 minus 7, which is negative 10 divided by 2 is going to be negative 5. Now, since you see that the roots have absolute values, both of them, which are greater than 1, all right? Both of them have absolute values which are greater than 1. This means that y is stationary. All right? So that's that. Okay, both roots have, and all of them have to have absolute values which is greater than 1. The absolute value of the first one is going to be 2, which is also greater than 1, and the absolute value of the second one is going to be 5, which is also greater than 1. All right, whatever comes out, you know, it has to be basically calculated its absolute value, and that's the way to do it, guys. Is it clear? All right, so yeah, and the process is going to be stationary, point blank, period. All right, and I'm going to show you another example. This process, okay, so that's going to be the second example. This is not going to be stationary. I just need to change the coefficient. So you have 1 minus 1.25, yt minus 1 minus 0.25, which is basically attached to yt minus 2. Now keep in mind, guys, a1 is going to be negative 1.25 this time, and a2 is going to be negative 0.25 this time. Always take the sign of these coefficients with you. All right, so therefore the Lag polynomial, since it changes the sign, is going to be 1 plus 1.25l plus 0.25 times x squared, let's say, but that's a pseudo multiplication, so I'm not supposed to say that. Is it clear? All right, so it changes the sign. All right, now if it's equal, basically if you take the roots of that, okay, so you have 1 point, sorry, this is, I was editing it right, but I hope it's basically it works. So 1 plus 1.25 times z plus 0.25 z squared is going to be equal to 0 if z is a root of the Lag polynomial. Okay, and I was just rearranging it. So here I was basically arranging that stuff. Now you multiply by 4 on both sides. You don't need to, so I was normalizing it, so that will be more consistent basically with the German approach, okay, that people learn in school. But that's basically what these coefficients are. I find it's more appealing, but that's just my taste. Okay, so I was using that, and so therefore a is going to be 1 according to the formula, b is going to be 5, and c is going to be 4. And if you put that together, minus b is going to be minus 5, okay, and then you have plus minus the square root of b squared, which is 25, then minus 4 times a times c, which is going to be 16. So 4 times 1 times 4 is going to be 16. So 25 minus 16 yields 9, and the square root of 9 is going to, so the discriminant is 9, and the square root of that is going to be 3. So you have minus 5 plus minus 3 divided by 2 then. The first root is going to be minus 5 plus 3 basically divided by 2. This is negative 1. And the second one is going to be minus 5 minus 3 divided by 2, which is going to be minus 8 divided by 2 is going to be negative 4. So negative 4 and negative 1 are the roots of the Lack polynomial. Now this does not imply that the roots are having absolute values which are greater than 1, because there is one root at least, okay, one root at least which does not satisfy that. Keep in mind, guys, that the absolute value of the second root, which is equal to the absolute value of minus 1, is equal to 1, and 1 is not greater than 1, of course. So not all roots have absolute values which are greater than 1. Therefore, the process is not stationary. Is it clear, guys? So you just need to find the roots of these polynomials. Actually, there is programs if you're kind of struggling with that, okay, how to find the roots. You can implement that if you like. So if you're kind of struggling with the functions, just try to implement those. I'm going to give you just, the fifth assignment actually is going to be about that. I will give you AR processes. So let's say this is going to be the first one, and then you would need to establish whether the process is stationary. Please explain why. Okay, so why first off, it can be only two answers, right? It's either stationary or not, but I want to have a brief explanation. So I say briefly, I was having no space, but try to do that briefly, so don't write all that stuff down. Okay, so you don't need to. All right, okay, is it clear? So I would like to ask you to do this. That's going to be the first process. This is going to be the second process. The first two are AR1 processes, as you see, so that's not going to be an issue, I think, but you would need to look it up. All right, now this is going to be an AR2 process. You have these coefficients, so kind of a similar approach, and so on. This is an AR4 process, as you see. Okay, so you have basically the Lack polynomial, which is going to be let's say the fourth order Lack polynomial, let's say, but there is a way to get around that. So this is going to be some sort of an equation. So if you watch carefully, that's going to generate an equation that's going to look like this: a times x to the fourth plus b times x to x squared plus c is going to be equal to 0. So that can be solved by a quadratic equation still. Okay, you probably know how to. Okay, so I want you to fight a little bit with that one. Okay, that is going to be also 10%. So of course they don't have equal weights. They do have equal weights, but that's just for simplification. This is going to be an AR3 process. Okay, right? So here, see what it's going to be like. Okay, so if you kind of not sure how to find these roots, you can run iterative programs with R if you're interested in that. Basically, I will give you a hint, so if you find it in general terms, that's going to be fine. 1 minus 0.2 times yt minus 1 minus 0.5 times yt minus 2. This is an AR2 process. That's going to be easy. All right, so you have sometimes, easy ones. That is also an easy one. This is also an easy one. Again, so you need to find these roots. The only issue is if you have complex ones. I'm going to show you how to deal with complex numbers a little bit. So I'm going to give you a hint, and then I would like you to look it up. This is an AR3 process. Look carefully. Maybe you can extract one or two roots already. Okay, so have a look, basically what the roots could be. And then as soon as you see the solution, you can tell what the process would going to be. So I want to have a brief explanation regarding stationarity. You should be efficient by the way. So, and that's that. Okay, so this is also a AR2 process, which is easy. All right, so you get 10 processes, and then you simply just examine whether they are stationary or not. And I want to have a brief explanation also. So you get 5% on your answer and 5% on your reasoning. Okay, for each. So that will yield basically 10% in total for one process, and then you have 10 processes, so this is how it's going to be. All right? Okay, guys, yeah, so, okay, let's see what's happening. Okay, the deadline is going to be not this Friday, not the coming Friday, the week after. This is going to be May the 31st. Okay, at 11 p.m. So you know how the rules are. And but keep in mind, guys, if the root, or let's say C is a complex number, of this structure, so you have a plus b times minus 1. Keep in mind, guys, that a is called the real part, okay, so that is going to be the real part, okay, or it's basically written like this, and b is going to be the imaginary part, although both numbers are real, okay, so a and b are real numbers, okay, but you have basically for the imaginary part you have minus b attached to it. So this is how it's going to look like on a complex plane. So you have the real part, you have the imaginary part, you have a here, and you have b here, and that's going to be basically your complex number. Keep in mind, guys, that complex numbers are defined in terms of vectors. So these are specific vectors on a complex plane. There is a vector addition and a vector multiplication regarding complex numbers, but every single one consists of two coordinates, let's say, a real coordinate and an imaginary one. And there is a specific rules of how to basically deal with complex numbers. Now, I would like to ask you to use basically the Euclidean norm when it comes to the absolute value. So this is why it's called Euclidean, because you might know this from the Pythagorean theorem. The length of this line, here you have basically a triangle, right? So this is going to be a triangle. If this has the length A and this has the length B, then the diagonal, according to the Pythagorean theorem, is going to be c squared, which is, let's not call it c squared, let's call it x squared, sorry, because it's not consistent with that notation. X squared is going to equal to a squared plus b squared. You know the Pythagorean theorem, right? Satz des Pythagoras. All right, so that's basically it. And then if you solve this for x, this is going to be equal to the square root of that. So this is called the Euclidean norm, and I would like to ask you to use the Euclidean norm when it comes to the absolute values of these complex numbers. Okay, so that's a formula that you would need to use, and I would like to ask you to do that. Okay, you don't use another norm. So this is going to be based on this one. Okay, if you use another norm, you might get a different result, which I don't want to. Okay, is it clear how to use it? So you have a complex part, you have an imaginary part, and then you would take that out, and I'm going to show you how to take it out, so how to deal with complex numbers, because there is going to be a proof on during this lecture, which I'm going to establish also. All right, keep in mind that the absolute value of a complex number, or the length of a complex number, because that's why it's called a norm. Okay, so this is not an absolute value, this is a norm, because keep in mind complex numbers are vectors, okay, in strictly speaking terms. Okay, so therefore we talk about a norm, and this is basically how you would address regarding the norm. Keep in mind that the norm of even of a complex number is going to be real all the time. Okay, so every single complex number has a real length, if you like. Okay, so if I say norm, you can call it the length of that vector, and I would like to ask you the Euclidean norm. So that's going to be basically the Euclidean distance. Okay, that's basically the term, Euclidean distance. There is also a different distance. Okay, the Euclidean distance is based on the Pythagorean theorem. Just for the record, so you understand, maybe you understand it better if I give you another one, so you see, because these norms are not unique. I'm going to also give you the Manhattan distance. Okay, so the Manhattan distance, you have been to New York, guys? You show hands who has been in New York. You've been to New York. Have you seen a map of Manhattan? How does it look like? Okay, basically it's looking like this, right? So more or less like this. All right, so if you basically want to go from A to B, let's say, you cannot cross it. Okay, so you cannot use basically a diagonal. That's not going to basically to work. Okay, so what you do instead is, I mean, unless you have a helicopter, right? So then you can use that one. But if you use the Manhattan distance, you have to walk. So first off on around this block, and then you go here. Okay, so if this is A and this is B, the Manhattan distance, okay, which I call X, is not basically what you have seen before. This is simply just, you know, the absolute value of A plus the absolute value of B. Then this is going to be the Manhattan distance. Okay, so that's called the Manhattan distance. Okay, maybe I add that term. Okay, because it kind of looks like the map of Manhattan, right? So if you walk around, this is how it's going to be. And again, the Euclidean distance, okay, the Euclidean distance, and in contrast to that, is, as I mentioned before, the square root of a squared plus b squared. All right? So that's in contrast. There is different distance measures depending on basically on the space that you are. And if you are in Manhattan, you cannot walk across the blocks, all right? Unless, I mean, if you fly, then you can, but maybe you don't get permission. You understand what I'm saying? Okay, so there is different distance measures, and I would like you to use, again, the Euclidean distance, okay? Not the Manhattan distance when it comes to that norm, the Euclidean one. Is it clear, guys? Okay, so that's that, just in contrast, so you know that there is different norms. Anyways, okay, now let's talk about basically stationarity processes, and I'm going to add triangle conditions. Triangle conditions are sufficient and necessary conditions for stationarity. This comes basically from the roots here that is generated from the Lac polynomial. I'm going to address them. So this is going to be stationary. There's a different way to establish stationarity for second order processes, and that's going to also be an option for you. So if you want to if you have second order processes, just check whether the so-called triangle conditions are satisfied or not. If they're satisfied, all of them, there are 3 of them, that basically the process is going to be stationary. And if just one is not satisfied, then the process is not going to be stationary. I'm going to show you what these triangle conditions are. The first triangle condition is that the absolute value of 2 is less than 1. The second triangle condition is going to be that a2 is less, strictly less than 1 plus a1. And the third is going to be that a2 is strictly less than 1 minus a1. This is going to be the triangle conditions. Why is it called triangle conditions? Because if you put those functions, okay, so you can basically use that one as functions into the a1, a2 plane. So you have basically these coordinates a1 for a2. Okay, so the combination is going to be, this is going to result in a triangle. And if you are inside the triangle, not on the triangle, inside the triangle, then the corresponding process is going to be stationary. Let me show that. So basically this corresponds to the to the third condition. So either, you're on the line or below, so you must be below that because that's going to be less. Keep in mind that the ordinate is going to be a2, okay? And that's basically what you have on the x-axis. So you're supposed to be below that line. You understand that, basically, the consistency? Now the blue one, of course, you're supposed to be below the blue line as well. This corresponds to the second condition, and that generates a triangle. If you use also basically the green condition, which I'm also adding here to it, then you'll have that basically, this is the lower bound here, okay? So that means here you have -1, all right? So, and then of course, if basically the absolute value of a2 is less than 1, then you are between these two, okay? So actually you are within that frame. Now, you don't need to have that one anymore, and the reason why the upper is not necessary anymore, because this is also implied by the other two. So this condition, I'm talking about that one, okay, that one, the upper one, all right, is also implied by those two, okay? So that can be skipped actually, but for the sake of completeness, because it looks nice, I added that too. If you put that together with that, this is what it's going to be. All right, so the absolute value is simply just that. And now this generates a yellow triangle here in the coordinate system. And if you are inside that yellow triangle, then the process is going to be stationary. And if you are outside that yellow triangle, for example here, if you are basically there, then the process is going to be stationary. If you are outside, let's say, so you are outside if, for example, a1 is going to be 1.5 and a2 is going to be, let's say, 0.5, then you are here. This is what it's going to be. You see that? Okay, if I'm not mistaken. So you are outside, then the process is not going to be stationary. It simply is. Understand what I'm saying, guys? Okay, so that's basically it. So as an alternative for your assignment, you can say the AR2 process is stationary because it satisfies the triangle conditions, and I would like you to show me that it does. Okay, so it's nice that you basically have figured it out, but just illustrate that. Okay, so if you want to use that, you can. I'm going to prove those, but before I do, I'm going to show you how to deal with that. So let's say you have this process, and then you check whether the triangle conditions are met. Okay, so for one by one, let's say the absolute value of A2, this is A2, guys, and this is A1, okay, and then you can simply ignore the additive constant, okay, so because that's not going to be important. A2 has an absolute value which is less than 1 because the absolute value of 0.1 is less than 1, that's true. Okay, now what about basically A2 being less than 1 plus A1? A2 is, of course, 0.1, and 1 plus 0.3 is greater than that, obviously, so 0.1 is less than 1.4, so the second condition is also met. And what about basically the third condition? The third condition is that A2 is less than 1 minus A1. A2 is 0.1, A1 is going to be 0.3, A1 is less than 1 minus 0.3, which is, of course, 0.7. So the third condition is also met. Every single one of them is met, so that means that this process above was or is stationary. Is it clear? So this is how it works. You can apply that for your assignment if you like. All right, yeah.
Is it applicable
only for AR2 processes, right? So that's what I wanted to basically mention. So keep in mind, if you have AR4, which sometimes you do, it kind of resembles to AR2. It's not going to work in general, right? Yeah, but that's it. Okay, now I'm going to prove that. It's not difficult to prove it, but it's kind of requires some techniques which you need to be a little bit, more sophisticated in that. So I'm going to prove the triangle conditions, all three of them. Okay, so if the process is stationary, this is what it's going to be. Keep in mind that the lag polynomial is before I do, okay, you got a question.
So if you want to check whether AR2 is stationary,
yeah,
either use the triangle,
yeah,
or this,
all the roots of the lag polynomials. Yes, either of the two. Yeah. So again, this is, if it's only, so it says literally, guys, okay, so let me remind you, here it is, if and only if. So the triangle conditions are both necessary and sufficient for stationarity of an AR2 process.
But we can use either this.
Sure, because again, read, please, if and only if. That's something that you basically need to understand. So stationarity is equivalent to the triangle conditions. If the process is stationary, then the process satisfies the triangle conditions. If the process satisfies the triangle conditions, then it's going to be stationary. This is a one-to-one relationship. If you're married to someone, then this person is married to you. If and only if. You understand what I'm saying? Okay? This is equivalent. So this basically automatically implies that you are allowed to use them if you like. Okay? But that's your choice. So you have basically two options in this regard. Either you calculate the roots of the lag polynomial, or you check whether the process meets the triangle conditions. But keep in mind, you are only allowed to use that for an AR2 process, not for an AR3 process, not for an AR4 process, for an AR2 process. And I would like to prove that. Okay, so I'm going to prove the triangle conditions. This is not difficult. Okay, but it requires some more sophisticated structuring. Okay, so the structure of the proof is going to be a little bit more inaccessible, but I would like you to understand it. Okay, now check it out. How do I prove the triangle conditions? You need to understand that the lag polynomial, if x is a root, so x is going to be the root of the lag polynomial a, then this satisfies that 1 minus a1 x minus a2 x squared is going to be 0. Now in this regard, what I want you to establish, or what I wanted to do is, I'm going to multiply every single, because if it's stationary, then the root is going to have an absolute value which is greater than 1, so x being equal to 0 cannot be a root. Okay, so that means that if you multiply basically every single expression by 1 by x squared, which I'm going to do, then this is going to yield 1 by x squared minus a 1 by x, and then minus a2, which is going to be 0. That's it. And then you substitute basically 1 by x by z. So this is going to generate another one, which is giving you z squared minus a1 times z minus a2, which is going to be 0. And this is another Lag polynomial. Okay, so, and that's what I basically want to try to establish here. Okay, so I'm going to multiply everything by 1 by x squared, and then in the second step, I'm going to substitute 1 by x by z. This is going to yield another, basically, structure of the lag polynomial, but it relates to it. So I'm going to show you what the relationship is going to be. I'm going to define as C, which is going to be just that. Okay, so C is basically abstracted from this approach. So again, how do you get C? Step number 1, you multiply everything by 1 by x squared. And step number 2, you substitute 1 by x by z. And then you have another lag polynomial, which is equivalent to the previous one. It's not the same, but it's equivalent one. Okay? If you look carefully, guys, check this out. Okay, so I want you to check it out. If the absolute value of z is greater than 1, then this is going to be equivalent to, not z, not because that's not what I wanted to use. I'm going to use x. Okay, so if the absolute value of x is greater than 1, which is basically equivalent of the process being stationary. Why? Because all roots of the lag polynomial, this is the original lag polynomial, must have absolute values that are greater than 1. This is going to be equivalent that the absolute value of z is less than 1. So if you take this polynomial, okay, the roots of that must be inside the unit circle. That's going to be a little bit more restrictive in that sense, and this is easier to deal with when it comes to calculation. So that has just practical reasons. You understand what I'm saying? Okay, if the process is stationary, then the roots of C must be inside the unit circle. That's what basically what I was making as a statement here. So you need to notice that Z, the absolute value of Z, is less than 1 if and only if basically the absolute value of x is greater than 1. So the process is stationary if the roots of A are outside the unit circle, and if the roots are outside the unit circle, then the process is stationary. So this is a one-to-one relationship. This is equivalent, right? You have seen this. Okay, and you can also say that if the roots of C are inside the unit circle, then the process is stationary. If the process is stationary, then the roots of C are inside the unit circle. Understand what I'm saying? This is a one-to-one relationship because C and A are not the same, but they are equivalent. Okay? If A has a root that is outside of the unit circle, that's going to be a root of basically of C as well, but that root is going to be inside the unit circle of C. You understand what I'm saying? So that's something that you need to understand. Now, why am I doing this? Because it's easier to deal with C directly than with A. You're going to figure it out. If you try to break it down, then you'll see this is going to be true. Now, I want to find the discriminant of C. How do you find the discriminant of C? What is a discriminant, guys? The discriminant is, according to the quadratic formula, b squared minus a, 4 times a times c. That's a discriminant. You understand what I'm saying? So if you look at this structure, you'll find that a is going to be equal to 1, b is going to be equal to negative a, and c is going to be equal to negative a, b is going to be equal to negative a1, and c is going to be equal to negative a2. So what's going to be the discriminant? The discriminant of c is going to be, and then you can see this here from that formula, b squared. Now this is going to be a1 squared, of course, and then you have minus 4 times a times c, and that's going to yield minus 4 times 1 times negative 2, which is going to be plus 4 times a2. This is going to be, that's going to be the discriminant of AC. Discriminante, you know that term? This is under the square root of the quadratic formula, guys. You understand what I'm saying? That's called the discriminant. And that's going to decide whether the root is going to be real or imaginary or complex, right? So it's going to be real if it's greater than or equal to 0, and it's going to be complex if it is less than 0. Because if you have something under the square root which is less than 0, then you have a complex number. You understand what I'm saying? This is basically generating the two cases. So again, the discriminant is looking like this, as I mentioned before. In the first case, if the roots are real, then the discriminant is non-negative. If the discriminant is non-negative, then the roots are real, every single one of them. Okay, in general there is 2, but you have at least 1. All right, is that clear, guys? And the case 2, if the roots are complex, then the discriminant is negative. If the discriminant is negative, then the roots are complex. So the roots are complex if and only if the discriminant is negative. Is that clear, guys? All right, so that's basically how it works. And I want to basically look at that case first, and then when I'm done, I'm going to look at the second case. So I'm just basically, discussing each of them. And I'm going to start by the first case, which states that the roots are real. So this expression, which is the discriminant, must be non-negative. All right? Now, this is going to be the equation. So keep in mind, guys, this is what it was. So let me remind you. Okay, so A, if you look at the quadratic formula, was equal to 1. B, if you look into the quadratic formula, was equal to negative A1. If I recall it correctly, yes. And C, if I recall it correctly, was equal to negative A2, then this is what it would be. All right, so if you put these together, this is going to be the solution of the quadratic equation, for which basically C is equal to 0. So that's going to be the root of C then. And that must be inside the unit circle. So I'm going to basically examine when is the case. Okay, so when is the root of Z inside the unit circle? And that's basically the case if the absolute value of that is going to be less than 1. So this implies, on the other hand, that Z is going to be between -1 and +1. All right, so that's exactly the case. Now, if you divide it by 2, and then you will see that this expression, okay, must be between -2 and 2. That's going to be the implication. Because if the numerator of the root is going to be between -2 and 2, then the root will have an absolute value which is less than 1. You understand that statement, guys? So the numerator must be between -2 and 2, and that's what you come up with. So this is basically what it means. So if the root is inside the unit circle, which is supposed to be, then -2 and then must be basically less than the numerator, and then the numerator itself must be less than 2. So that means that the numerator here of the root is going to be between -2 and 2. You understand why? Again, so if you solve this equation, -1 being less than the root, then and then +1 is also being less than +1, right? You see that you have basically 2 down there. So if you put in this expression, okay, so inside here, and then you solve this for the numerator, then you have -2 on the left hand side and +2 on the right. Is it clear, guys? So the numerator of the root must be between -2 and 2. And I'm going to basically examine these two cases. The larger root, okay, is bounded, of course, if it's larger, the larger one is going to be bounded by 2. So whatever the larger root is, it's going to be basically based on that. Okay, so you have basically bounded by 2 from above. So this means I'm going to look at this case. So whatever this is, and the larger one is going to be yielded basically by using plus. Why? Because the discriminant is greater than equal to 0. That's the reason. All right. So the larger one is going to be obtained if you use plus in a quadratic formula, and the smaller one, the smaller root, is going to be obtained if you use minus in the quadratic formula. And the larger one cannot be greater than 2, and a smaller one cannot be less than -2. These are the two cases that I'm going to look at, and according to that, I'm going to basically solve the corresponding inequality. Okay, so I'm going to solve this basically for A2 then, okay, because A2 is in the on the y-axis. Now, how do you get that? Now, the first step is easy. So the only thing that you need to mind when it comes to inequalities is that if you multiply on both sides by negative numbers or divide by negative numbers, then the inequality sign would change, okay? Or, I mean, in general terms, if you apply a strictly decreasing function on sides of the inequality, then the inequality sign would change. But other than that, it's not a big deal. Okay, so in this case, the square root is going to be less than 2 minus a1, which is obvious. Okay, now how do you get rid of the square root? You can square on both sides. If you do that, this is going to be equivalent in this case. Why? Because you find that under the square root you have the discriminant, of course, and the discriminant is going to be non-negative. So if it's not negative, it's not going to be an issue. Okay, so if you take basically for example, the square root of 5, and then you would square it. This is going to be 5. So you can get rid of basically that relatively easily. And since the discriminant is non-negative, you don't need to consider the other case, right? So therefore, this is going to be equivalent, okay? And the inequality sign would not change, so I'm simply just getting rid of it. And then I will take that to the second. Now, if you take that to the second, this is going to be 4 minus 2 times a time 4 times a, a1, and then plus a1 squared according to the binomial formula. You know that a minus b to the second is going to be a squared minus 2 times a times b plus b squared, right? So that's basically that, which I'm going to use here. And then yeah, you see that basically you can get rid of a1 squared, so you take that out, and then you divide by 4, and then you solve the inequality for a2, and that's what I did. And if you do this, then you got a2 is going to be less than 1 minus a1, and this condition is, as I remember, the second inequality condition of the triangle conditions, right? So I think, if I recall, no, the third one, I recall it correctly, but it doesn't really matter. So one of the three, right? So we have basically, which I have already established here. Is it clear? Okay, so that's the one condition from the triangle condition that I'm going to establish. The second one is going to be obtained if you, the smaller root, okay, smaller. I need to re-edit. The smaller root is bounded by -2 from below. I apologize, I forgot to edit that. The smaller one, not the larger one, the smaller one, okay? I'm going to re-edit the slide, I apologize. But anyway, so this is the part of the inequality that I'm considering in the next step. You understand that, guys? And I'm going to do the same thing. And that this will yield the other inequality condition that was missing. Basically, that's going to be the third. So you have -2, which is less than the square root of that stuff, right? So one, or the numerator, sorry. So you have minus here, because if you do minus, you're going to get the smaller one. Why? Because the discriminant is non-negative. That's why. That's the reason, all right? So the discriminant is non-negative, so whatever you see here, this expression will be non-negative as well. And if you have basically a1 minus that non-negative expression, this is always going to be smaller than a1 plus a non-negative expression, no matter what a1 is. So even if it's negative or positive, it don't matter, because if you take a non-negative number and you subtract that from it, that is going to be smaller even. You understand? So it doesn't really matter. So that's going to be basically the lower bound of the smaller root, not the larger root. Sorry guys, I apologize. And yeah, so you do the same stuff. Now you need to rearrange it, because I will bring basically that one to the left hand side and +2 to the right hand side. So you have basically the square root, which is less than 2 plus a1, and then you square both. Okay, so again, you square both. This is something that you can do because the discriminant is not negative, and that will not change the inequality, and this is going to be equivalent, by the way. So you can go backwards also because of this condition, okay? And if you square that, then you simply apply the binomial formula. A plus b squared is going to be a squared plus 2 times a times b plus b squared. Then you see that a1 squared is on both sides. You simply just subtract from both sides of the inequality, and then you divide by 4. Even if you divide by 4, the inequality sign will not change. So that will yield the other condition. I think that was the second condition from the triangle condition. So we have established the second and the third conditions, and then we just need to establish the first condition. This is going to be based on the issue where the roots are going to be complex. In this case, it was real, and then in the second case, there's going to be complex roots in general, where one root is going to be the complex conjugate of the other. But that's just a side note, you don't need to know this. Again, this is the second condition of the triangle condition, so there is just one condition is missing, and that is going to be attained from the second case. So we need to understand that the conjunction of the two also implies basically that a2 is going to be less than 1. How come? Add basically these two inequalities. So if you do that, you can, okay, this is allowed. So this means that 2a2, you add both sides, is going to be less than 2. So 1 plus 1 is going to be 2, right? And minus a1 plus a1 is going to be 0, right? So that's that. And so you simply solve this for a2, which means that a2 is going to be less than 1. So the two conditions imply that a2, whatever it is, it will be less than 1. Understand what I'm saying? That's absolutely necessary, because if it's not, then the process cannot be stationary anymore. The two conditions need to be satisfied as well. I will use that, okay? So this is 1/2 of the other condition, and the only condition that is missing is that I need to show, okay, so I still need to show that a2 is going to be greater than -1. This requires but a little bit more sophisticated approach. So that's the only condition that is missing. So if I show, in addition to that, the two conditions, that one and that one, will yield the first condition of the inequality, which means that the absolute value of a2 is less than 1. If a2 is greater than -1 and less than 1, then the absolute value of a2 is less than 1. You understand what I'm saying? So that's going to be the plan. So my plan is just to show, this is what we left, okay, so that a2 is greater than -1, strictly greater than -1. All right? Is it clear, guys? So that's basically that, and I'm going to finish the proof by doing so. But this is going to be obtained from the second case, where the roots are not real, the roots are complex. In case of complex roots, the discriminant is negative. Now, how to deal with that? So whatever you have, basically, I'm going to use the following thing, just to show you, okay? So let's say you have something under the square root, where basically, which is negative, okay? So let's say x is going to be negative. How to deal with that? Now, I'm going to show you. So you see basically that this is going to be -1 times -x, right? So -1 times -x is simply x, not a big deal, all right? Now you can split the roots, okay? So you have the square root of -1 and then the square root of -x. And this is basically the imaginary part, which I call I, all right? But keep in mind, guys, that -x is going to be positive if x is negative. So if x is negative, then -x will be positive. So this means that this stuff here is, okay, so I use a different color. Sorry, I want to be a little bit more consistent. This stuff here is going to be the so-called imaginary part of a complex number. Keep in mind, guys, that every complex number has a real part and an imaginary part. Both are real, but the imaginary part is attached to basically to I, where I is equal to the square root of -1. Okay, so every complex number there is consists of two parts. You have a real part, which I write it like this, and then you have plus I, all right, times the imaginary part. And this is how you basically break down every complex number. You understand what I'm saying? So this is what it's going to be, and I'm just going to do that. Don't worry. So it kind of looks difficult. So I multiply, basically, I take it out, and this means if the discriminant is negative, then this expression under the square root is going to be positive. So that total expression is going to be the imaginary part, and then you need to take out basically I from the square root, which I just did. Okay, so keep in mind, guys, that's what I was doing. So the square root of x is going to be equal to I times the square root of negative x. That's what I was doing. You understand what I'm saying? So simple is, okay, if x is negative, which it was the case because of the discriminant is less than 0, then -x would be positive then. You understand what I'm saying? So this is a trick that I use, so I can deal with these expressions. And if you see that, this is the real part. Okay, so this part is the real part of the complex number, and the other part, the whole thing with the square root, is going to be the imaginary part of the complex number, and that is going to be it. And if you want to calculate the absolute value of a complex number, which I'm going to do, then this is simply just a sum of the squares of the real part. Okay, so the real part to the second, yeah, and then you have the imaginary part to the second. So you simply just, square those. They're both real, so you square those, and then you calculate the square root of that stuff and check whether a1 is going to be greater than -1, which I'm going to do. All right, so that's basically the idea what I was using. Every single complex number, if you use the Euclidean norm, is going to have the absolute value like this. Okay, so that's what I was showing you. Okay, so the absolute value of that is going to be the square of the real part plus the square of the imaginary part of the complex number. And you don't need to deal with basically I anymore. Keep in mind that I equals the square root of minus 1 in this case. You understand what I'm saying? So that's basically how you deal with that. And I would, okay, so how do I basically break that down? That's not going to be an issue anymore. The square of a1 by 2 is going to be a1 squared by 4. That's that. And the square root of this expression, now if you, not the square root, sorry guys, the square of this expression. Now you simply get rid of the square root. So you have the discriminant. Okay, or minus the discriminant, so you have basically minus the discriminant, okay, and then by 4. Okay, keep in mind guys, this expression is the discriminant, you find it here is negative, so you have basically two numbers that you add, and that's what I'm going to do. Okay, so I'm going to put this is the common denominator, so luckily as I am, and I basically get rid of, as you see, I'm going to get rid of a1 squared in both cases. So a1 squared minus a1 squared is going to be 0, and you're just left by 4 times a2 by 2, which is going to simplify to the square root of a2, and that's that. So this is going to be the square root of, minus a2. I forgot the sign here. Minus a2. And that's it. Don't worry about it. Square root of minus a2. You need to understand that since basically this is a real number, okay? So that is going to be a real number all times, no matter what. Absolute values are real. So that means that basically the square root of negative a2 is also a real number. You understand what I'm saying? So this means, and this is basically what is based on that, this can be only real if a2 is accordingly, if it's basically, it would be positive, then it would not work. So this is basically would yield a negative expression, but that's something that you would need to do. Now, if basically a2 is greater than 0, okay, which let's say this is going to be the case, that's going to be the first part, then the absolute value of that is simply just that, okay, so you can basically break it down simply, and then minus a2 is less than 1, as you see in this case. So if minus a2 is less than 1, this is basically the condition, or you could say a2 is greater than minus 1. So if a2 is greater than minus 1, this expression would yield basically a2 is going to be greater than 0, okay, but that's something that you would need to understand. And if a2 is less than 1, which again, where is this coming from? This is coming from the conjunction of the previous two conditions, and this yields basically the other one, and that will yield also together. So combine the two, okay, yields this condition, and that's what is basically would have. All right, so this is, if that would be the case though, but that's something that you need to think about. All right, and so this is showing the first condition of the triangle condition. So I basically was showing everything from that, and that's basically what it was. All right. Now, if you look at the ARP process, which is looking like this, so the stationarity of that, this is going to reveal. This is what the Lac polynomial would be. If it's stationary, there is one thing that I wanted to mention here, and that's going to be short. And for the next time, I'm going to address the U-Walker equations, so I'm not going to do that now. But if it's stationary, then this means that if basically z is a root, then this means that the absolute value of z must be greater than 1. This can be only achieved if z is not equal to 1. So 1 cannot be a root of the Lac polynomial. Okay, so the point 1, point 1 cannot be a root of the Lac polynomial. You understand that, guys? Why? Because if it was, then not every root would have an absolute value which is greater than 1. You understand? So this is not basically would work. You understand? So this is basically one conclusion. 1 cannot be a root of the Lac polynomial, because if it was, then the process would not be stationary. Why? Because not every root would have absolute value which is greater than 1. All right, you understand? Now, this means that 1 cannot be a root. Okay, so if you put in 1 into the Lag polynomial, you cannot get 0 out of that. It's going to be impossible. If it was 0, then the process would not be stationary, guys. You understand? So if the process is stationary, then every single root of the Lag polynomial has an absolute value which is greater than 1. Okay? Every single one of them. So if there is a root which does not satisfy that, which would be 1 then the process would not be stationary. Is it clear? All right. So you need to understand this. Now, this means that basically if you put that in, this expression cannot be 0. And if you just simplify that by using the sum notation, this reveals that the sum of these coefficients, so whatever these coefficients are, the sum of these coefficients cannot be equal to 1 if the process is stationary. All right? So, but keep in mind, guys, this is necessary. Okay? This is necessary for stationarity, but not sufficient. Okay? But not sufficient. So, this means what? If the process is stationary, then the sum of the coefficients cannot be equal to 1. You understand what I'm saying? But just because the sum of the coefficients are not equal to 1, the process is not necessarily stationary. So you cannot reverse it. You understand what I'm saying? So stationarity, okay? So stationarity implies that. Okay? That means that if this is not true, then the process cannot be stationary. You understand what I'm saying? But if it is true, and that's something that most students fail to understand, if it is true, then it doesn't necessarily mean that the process is going to be stationary. It can be stationary or not. You understand what I'm saying? So if, let's say, statement A implies statement B, then you know that the negation of B also implies the negation of A, right? But B does not imply A just because A implies B. So you cannot reverse it, necessarily speaking. Understand what I'm saying? Okay, if A implies B, then B is sufficient for A, but not, A is sufficient for B, and B is necessary for A, but not sufficient. Okay, so condition B is necessary, but not sufficient for A. You understand what I'm saying? So stationarity implies that the sum of the coefficients cannot be equal to 1. If they are, then the process cannot be stationary. But if they don't, then the process is either stationary or not. You understand what I'm saying? So you need to be careful. But maybe you're lucky. You understand? So maybe you're lucky. I'm going to basically extend this a little bit. So and this is not only true, basically, this is also true that it is less than 1. So the sum of the coefficients is less than 1. What does that mean? That means that past observations, so the impact of past observations, are not disproportionate for future observations. If it's greater than 1, let's say the error is 0, that the process is going to be explosive on average. Understand what I'm saying? So if it's greater than 1, the process is going to be explosive. Why? Because past observations, okay, have a higher impact than 1 basically on a current observation. So that's going to be explosive. The process is going to be explosive. You can use matrices, especially eigenvalues, if you know the term eigenvalues of matrices. I don't know if you heard that term. So I could show you that one. But let's say if the sum is greater than or equal to 1, the process is going to be explosive. If the process is explosive, then it's not going to be stationary anymore. All right? So you need to understand the expectation of the noise is 0, right? So the expectation of the noise is 0 at all times, right? And if the sum of these coefficients, okay, if the sum of these coefficients, all of them, is greater than 1, let's say, or equal to 1, if it's equal to 1, it's going to be a so-called random walk. But if it's greater than 1, then the process will tend to explode, okay, past observations disproportionately impact basically the current observation, so it's steadily growing because it's exponential, right? So that's basically what it would be. All right, guys. But keep in mind this is necessary, okay, but not sufficient. And this is important. Not sufficient for stationarity. All right. So if it's true, if the sum of the coefficients is less than 1, then there is still the possibility that the process is not stationary. Understand what I'm saying? It's very important. Okay? But if it's greater than 1, then the process cannot be stationary. Or maybe you're lucky, guys. You understand? So if you're not sure, you can check. Okay, so sometimes maybe you are. Okay, so implication, if the sum is greater than or equal to 1 of these coefficients, then the process cannot be stationary. Never. Okay, so but this is an implication. This is not sufficient for stationarity on the other hand, right? So this condition is necessary but not sufficient for stationarity. You understand the term, guys? Okay, so this is another one-to-one relationship. Okay. Okay, just because your wife is cheating on you, it doesn't imply that you are cheating on your wife. You understand what I'm saying? Right? So this is not a one-to-one relationship. But if it was one-to-one relationship, that would be the case. You understand? Or just because you're cheating on your wife, it doesn't mean that your wife is going to cheat on you. Okay? Okay, so if A implies B, then B does not necessarily imply A. You're laughing, all right? Okay. I'm not sure what you're laughing at, but anyways, you seem to be more experienced than I. Anyways, okay, so let's see, for example, this one. This is a AR5 process, as you see, and the AR5 process. Now, look at these coefficients, okay? So simply take the sum of these coefficients. You might be suspecting something. If you are summing them up, which I did, you find something that is going to be equal to 1. If the sum is equal to 1, no way that the process is going to be stationary. No way. All right? If it's greater than 1, it's even worse. Okay? So for stationarity. So maybe you're lucky, guys. Okay? But let's say, if it was less than 1, okay, that you cannot establish stationarity, because that's only a sufficiency, only a necessity, but not a sufficiency for stationarity, guys. All right? I hope you understand this. I don't have time for the Walker equation, which I'm going to basically skip for this part, so I'm going to consider that in the next lecture, which is going to be 10. And yeah, that was it for today, actually. All right? You have questions? Yes.
I have maybe a stupid question, but how do we...
I'm going to give you maybe a stupid answer, so yeah, please.
How do we know that C is a complex number?
You'll see, because the discriminant is going to be negative.
So just from...
You understand? So maybe you're not sure about this, but let me give you a quadratic equation. Okay, so let's say, okay, this is nothing to do with that. So let's say you have a quadratic equation. Let's say x squared plus x, I don't know, whatever, plus 2 is 0. Okay, so let's take that. And what is going to be the solution? Minus b is going to be minus 1 plus minus b squared, which is 1 minus 4 times 8 times c divided by 2. So this is going to be minus 1 plus minus the square root of 1 minus 8, if I'm not mistaken, which is negative 7 by 2. So this is a complex number, obviously, because the discriminant is negative. So how do you know that? Now you know. Okay? You need to have the real part and you need to have the imaginary part. That's basically it. Yeah. All right? Is it clear? Okay. Yeah. So that's that. Okay? Anything else? You will know. So you'll see it's going to be a complex. So then you need to take the imaginary part, you need to take the real part, and from those two, you need to calculate the length of the complex number. All right? Anything else? No? All right, so there's a new assignment out. Don't forget the old one. Okay, so please, I mean, I heard that people are having trouble sending me an email with the attachment because the server of the university does not accept Excel files or other than PDF files for security reasons. I don't know why there are. So maybe you can send me a link from a file host if you want to send it via email. But I actually recommend that you send it via Telegram. It's easier for me even to edit it. So I want to basically edit your files and yeah, maybe kind of ask you to send it on Telegram instead. But if you don't like it, then you can send me an email. But if you send it on basically using an email, please use a file host, maybe a drive or folder or something like this. Okay guys, yeah, that was it for today. Take care. Thanks.